So when the velocity of projection increases, range also increases. Range is also directly proportional to cosine of the angle of tilt or inclination. Meaning when the angle changes, the cosine of it, which is the horizontal, would also change and so would affect this. Then the range also is affected by the time of flight. When you increase the time of flight, range can also increase. When you decrease it, it won't. So let's only dwell on this. If the range depends on the cosine of the angle, here we can simply say that R depends on theta. There is cos theta because we are only interested, the range occurs horizontally, not vertically. That's why we are taking cosine. But R is directly proportional to the angle of the inclination. Meaning that different angles would give us different maximum horizontal distance traveled by the body. Please, are we okay? Different angles of inclination must give us different values of the horizontal distance traveled. So if this is a body being projected at an angle to the horizontal, this is theta. Bushra, mute yourself for me. So when I change this, the body's horizontal distance traveled, which is the range, this is ground to ground, can also change. R can also change. Okay, so different angles would give you different horizontal distance traveled. Out of the possible angles, you see, when the angle theta is 90 degrees, here we are talking about vertically upward motion. We've gone away from projectile motion, and we are looking at vertically upward motion. Please, when you come in, mute yourself, okay? So the moment theta is 90, it's no more projectile motion, it's vertically upward motion. So the range projectile motion shall be between 0, okay, in between 0 and 90. Now, we experiment, okay, has revealed that the only angle that will give you a maximum horizontal distance traveled by the body is when theta is equal to 45. So when theta is equal to 45, the projectile can go through a maximum horizontal distance. And this is what we are describing as a maximum range. So maximum range of a projectile occurs when the angle of projection theta is equal to 45 degrees and no other angle. Please, are you okay?
Yes, please.
So the question back to the class is that when do we have or when can we obtain maximum range in a projectile motion?
Mr. Dear.
Yes, it's a question.
Please, can you repeat what you said about the maximum range occurring something 45 degrees?
Okay, I'll pick it, but pay attention. What I'm saying is that because R is directly proportional to theta, the angle of inclination, it implies that different angles would give you different horizontal distance traveled by the body. Now, experiments and theory, okay, have proven that we have maximum horizontal distance when the angle of inclination theta is equal to 45 degrees. So we obtain the maximum range when theta is equal to 45 degrees. Arezi, are you okay?
Yes, sir.
So when theta is equal to 45 degrees, maximum range. So practically, if you want to shoot an object, okay, when you want to project an object to go very far, then your angle of tilt must be, the object must be given a velocity of that amount of velocity, okay, making an angle of 45 degrees to the horizontal. And this is the only condition where the object can go very far. So it is even applied in warfare. If if military people want to hit a target, then the bullet must be directed at an angle of 45 degrees to the horizontal, and that they can be able to hit the expected target. So maximum range, okay, when theta is equal to 45. Now let's look at the expression we got for the range. Yesterday we saw that range is equal to u squared times sine 2 theta over gravity. Now when theta is equal to 45 degrees, R would be equal to u squared sine of 2 times 45. Theta is 45, so I'm substituting at the angle. So u squared times sine of 90 degree divided by g. And since sine 90 degrees is equal to 1, then it means that R is equal to u squared over g. And class, this is the relation for maximum range. So when you want to calculate for the maximum range is simply equal to u squared, the square of the velocity of projection, divided by gravity. Any question? Class, any question? So that's it. So the difference between range and maximum range is that range is the total horizontal distance traveled. But when we talk about maximum range, we are looking at the angle that can, that can give us the highest possible horizontal distance. And if you always want to obtain the highest possible or the maximum possible horizontal distance, then gauge or give the velocity an angle of 45 degrees to the horizontal, and it can go very far than all other angles. Is that okay?
Yes, please.
Okay. Now, one other thing I want you to pay attention. We are looking at when it's ground to ground. There's a velocity of projection u. Please, we saw that at every point, when the body is here, before getting to the maximum height, the body has a horizontal velocity and a vertical velocity. If your question demands that find the velocity after, find velocity after maybe 2 seconds of projection. 2 seconds of projection. The statement that find the velocity is not enough to determine whether it is a horizontal velocity or a vertical velocity. Because, let me give, can I clean this side? Can I clean this side of the range, maximum range?
Yes.
Okay.
Yes.
Yes, please.
Maybe an object is projected at an angle of 60 degrees. Theta is equal to 60 degrees. Then maximum the velocity of projection u is 100 meter per second. And the question is that maybe determine the velocity of the body after velocity of the body after 1 second of projection. So after 1 second, what is the speed of the body? You see, the question is that determine the velocity, but the question is not specific. Which of the velocities? We have horizontal velocity, we have vertical velocity. Here we are not so clear which of the velocities. Or you are okay. Are you so clear with the question? Class, are you? I am not. Good.
Yeah.
So you are clear. If you are clear, then solve the question. You see, so the statement is not so clear. Which of the velocity? Is it the vertical velocity? Is it the horizontal velocity? And this is where the issue is. Okay. Now, before you can solve the question, you have to determine the time taken to reach the maximum height. After 1 second, is the body at the maximum height? If the body is at the maximum height, then the only velocity there will be equal to what? After 1 second. No, after 1 second, if the body is at the maximum height, then the velocity there will be equal to, yes, somebody said 0. It's a no.
1.
The initial horizontal velocity.
The initial horizontal velocity, because let's assume this is the maximum height. If this is the maximum height, Vy is equal to 0. But since velocity, the horizontal velocity is there, u cos theta is there. So you have to find the time taken to reach the maximum height to be sure whether after 1 second we are at the maximum height or not. So using T is equal to U sine theta over G. U is equal to 100 sine theta 60 divided by gravity 10. Sine theta sine 60 is 0.866 or root 3 on 2. So you have 50 root 3 divided by 10, and this is 5 root 3. What is 5 root 3? Give me the answer in decimal figures. 5 times root 3.
8.66.
So 8.66 seconds. So it means that after 1 second, the body is not at the maximum height. If the body is not at the maximum height, then it means there are two velocities acting on the body, the vertical one and the horizontal one. Please, class, I hope you are following.
Yes, please.
How then do we find this velocity after 1 second? The horizontal one is u cos theta, and this is 100 times cos of 60, and this is 50 meter per second, because cos 60 is half. The vertical one can be determined by v is equal to u sine theta minus dt. U sine theta 100 sine of 60 minus 10 times, and this is where you have to make use of. So we want to determine the velocity, vertical velocity at this time, 1 second. So t will take 1 second, because you need the velocity at that time. This is 100 times root 3 on 2, 50 root 3, and 50 root 3. Oh, okay. We just had 8 points. Now check for me. This will be 50 times root 3. What is 50 times root 3? Let's divide by, so it won't be
56.602.
okay. 56, right?
86.
All right, 86.603.
603.
Okay, so minus 10, and the velocity will be 76.6 meter per second. So after 1 second, the vertical velocity is this. The horizontal velocity is this. So that's what is happening. After 1 second, the body is here. The velocity here is equal to 76, 50, and then the velocity here will be 76.6. Okay. Now when you have two velocities, here the angle between them is perpendicular. Once the angle between them is perpendicular, we use Pythagoras theorem, because we can create an equal vector of this and put it here. When we draw a line, when we look at, we start vectors, you understand. A vector, equal vectors have the same magnitude, direction, and are perpendicular in space. So equal magnitude as this one. So 76.6, the same direction as this one, so that the order of the vectors go this way. Follow a triangle. We have a triangular law of vectors. Please, when we will start vectors soon, and you understand this and this, and because they are perpendicular, the resultant will be this. Okay, so this forms a right angle triangle. So if this is going here and this going, then the shortest possible distance will be this. This will become the resultant vector or velocity. So if I want to determine this, this is equal to, using Pythagoras theorem, v squared will be equal to this side squared, which is 50 squared plus 76.6 squared. I put them together for me, 2500 plus, what is 76.6 squared? Find out some everything and take the square roots for me. So v will be equal to 76.6 squared, add to 2,500.
Please, I got 91.474.
Okay, 4, 7. So 91.5 meter per second. And this is the velocity after the velocity of the body after 1 second. So if the question just says that find the velocity and the question after so and so seconds, and the question is not so clear with vertical velocity, horizontal velocity, then they are interested in the resultant velocity after 1 second. Resultant velocity after 1 second. And this is the resultant velocity. Another thing you have to pay attention to is that, you see, in projectile motion, the angle, this two-dimensional projectile, the angle isn't constant as the body goes. It's not fixed. Here we are told it is 60. Now, look, the path or the trajectory is parabolic. It's not a straight inclined line. As the body goes up, the path to the horizontal bends downwards. It's like this, gets to the maximum height, on and on. So if I take any position of the object, here the angle is 60. As the body goes on and on, the angle drops. So the angle here is not the same as what is here. So the angles are also not the same because it isn't just a straight inclined line. It's a curvy kind of thing as the body moves on and on. So the angles are not the same. A question can be given where these varying angles, okay, can be applied in a question. Okay. Now what I will do is that as we move on, I'll be giving you different questions to see what you can do. Then I take the time to explain and then solve for you. Is that okay? So I'll get questions to this effect, give it to you, you try, then I take the time to take you through the solution. Please, is that okay? Are we fine?
Somehow.
Which part of it is there somehow? Let me know your somehow. All that I'm saying here, go ahead.
Yeah, please, when you cited a question and then you saw for the time and then you said it means it hasn't reached the maximum height. Like, how did you?
Okay, you see, how did I come to the conclusion that the body hasn't gotten to the maximum height yet? Is that the question?
Yes, please.
Good. Please, another opportunity for you to understand better. Quick one. So this is motion. I'm told the velocity of projection makes an angle of 60 degrees to the horizontal. The velocity of projection itself is 100 meters per second. And this will be the path or the trajectory of the body. So this is ground to ground. Yaba, are you there?
Yes, please.
Okay. So this is ground to ground. It starts here and drops at the same level, ground to ground. I'm assuming this is the maximum height. So when it is here, at this point, dy is 0. The horizontal velocity at every position of the object is constant, u cos theta. So if the question, let's assume after 1 second the body is here, but I have to determine whether the body truly is here or is at the maximum height. what will inform my decision? I can calculate the time taken to reach the maximum height. And I know the time taken to reach the maximum height is u sine theta over g. Are you okay? So this will
Yes.
help me get the time taken to reach the maximum height. Then when I get that, I compare it with a given time. So I know u 100. Sine of the angle of projection is 60. So sine 60 divided by gravity, which is 10. Appear sine 60 is 0.866 and some coins. So or sine 60 times 100. Okay, and that will give you 8 yes, 8 points, because sine 60 is 0 point. Okay, or this is what you have. Since sine 60 is 0.866, this will cancel it times 10. So the answer will be 8.866. Okay, and what this means is that it will take the particle 8.866 to get to the maximum height. Okay, meaning that if you have to calculate the velocity of the body after 1 second, then it means after 1 second, the body is not here because the body will take this time to get to this point. So if 1 second, then the body is still between this point and this point, not even half of it, half of this time. Please, are you okay?
Yes, please.
So this is what informs us that after the given the time in question, the body is either at the maximum height or not. Any
Yes,
further
please.
question? All right.
No, please.
Thank you. Please, to the rest of you, if you have some concerns, do not show it. Come out, okay? This is our lab to help ourselves, okay? Energy of a projectile. The energy of a projectile. The energy of a projectile. You see, as the body goes up, what happens to the velocity? Yes, as the body, it decreases. So if the velocity is decreasing, what do you think would happen to the kinetic energy of the body?
It would also decrease.
It will also decrease because kinetic energy is the energy. Complete it for me. Kinetic energy is the energy
of a body.
uh, okay. So energy of a body by virtue of its motion when the body is moving. So it has a good thing to do with the velocity. Now, as the body goes up, what do you think would happen to its potential energy?
Maybe
What do you think?
increase.
It will increase.
Is it maybe or it will increase?
It will
It will
increase.
increase.
Why do you think it will increase? Why?
Because potential energy deals with the position of the object. So
Exactly. And it deals with height of the object within the gravitational field. Okay, so if this is the surface of the earth, Yaba is here. Aquia you are here. Because this is your best position from the surface of the earth. This is Aqua's position from the surface of the earth. Because Aqua, okay, has a greater height within the gravitational field which affects everybody. Yaba and Aqua Aqua's gravitational potential energy will be greater than this. And gravitational potential energy is the work done in moving a body from one point to another point. That is what it means. The work done in moving a body from one point to another point. So if a queer has a mass m, the work done by a queer is equal to force times distance. The distance here is the height. This is h2. So for a queer's work done is force times h2. How do we determine the force? Yes, class, how do we determine the force exerted on a queer? It is a queer's mass
Times
the
acceleration.
acceleration due to gravity, because both of them are within gravitational field in air. Okay, so times g times h2. And so the work done is mg times h2. But I just said that the work done in moving a body from the surface of the earth to a point, another point within the gravitational field is the gravitational potential energy P. So that's how come we conclude that potential energy is equal to mgh. It's simply the work done in moving a body from one point to another point within the earth gravitational field. Please, is that okay?
Yes.
Okay? So potential energy has to do with height above the surface of the earth. When the body is here, its vertical displacement is maybe h something. When the body gets here, the vertical displacement on the surface of the earth or on the horizontal is equal to this h1, h2, meaning that the body possesses a greater potential energy at this point than when it's here. Do you agree with me?
Yes,
Yes.
please.
Then when it gets to the maximum height, the potential energy is maximum. So as the body goes up, its kinetic energy will be decreasing, but its potential energy would also be what? Increasing. However, if we choose 2 points, when the body is here and then when the body is here, the total energy possessed by the body here and the total energy possessed by the body here must be the same, constant, conserved. So as it moves along, kinetic energy decreases, potential energy increases. But at every 2 points, the total energy possessed by the body must be conserved or constant. Is that okay? So let's go through the mathematics of what we are saying. Let's look at the body at the maximum height and the body just before, okay, just few seconds after projection. Few seconds after projection. What do you think will be if the body just begins to move? What do you think will be the energy possessed by the body here? The total energy. What will be the total energy?
From the beginning.
Just few seconds, okay, after projection.
0.
Once it can be 0, the energy over here will be equal to the kinetic energy, because here we are assuming that it hasn't covered much vertical height, even though there will be something. I don't dispute that, but because we are looking at the energy there to be maximum kinetic energy. So at this point 1, the total energy here will be equal to half mv squared. Okay, and this is equal to half v will be u, that constant horizontal velocity over here. Okay, so u cos theta squared. We are not seeing, we are just looking at the body just beginning. It hasn't moved that much, very, very, very small movement. That's why we are only looking at that the velocity here to be equal to the constant horizontal velocity. We are overlooking that little vertical velocity. Please, are you okay?
Yes, please.
So at 1, this is it. Now let's look at when the body is at the maximum height. At the maximum height, Vy is equal to 0. So we are considering 2 points, this point and then this point. Okay. So at 2, or at the maximum height, okay, the body will possess kinetic energy, because the velocity, there is some horizontal velocity acting on the body. So the total energy there is equal to Ke at that point, which is half m. The velocity there is this, because Vy is 0. So u cos theta squared, and this is equal to half mu squared cos squared theta. This cos squared theta is the same as cos theta squared. Okay. Now, at this point, is there another velocity at the maximum height? Is there a second velocity to it, to the body? Oh, sorry, energy rather. Will the body possess another energy apart from the kinetic energy?
Yes, please.
And what's that? What's that energy?
Potential.
Good. So there will be potential energy, which is given by the mass of the body. Please let me take a quick call and then get back to you. Okay.
Yes,
Yes,
please.
please.
All right. Okay. So the potential energy would be mg H. But what is the H? How do we get the H? Yes. How do we get the H?
I think is the H the maximum height.
Good. Good. So here, the maximum height H must be equal to U squared. Don't forget H max, maximum height over here is equal to U squared, U sine theta all squared over 2G, isn't it?
Yes,
So
please.
U squared sine squared theta divided by 2G. Then you realize that this and this will cancel, and the potential energy is mu squared sine squared theta divided by G. So if you are looking for the total energy, E total possessed by the body at the maximum height, we have the kinetic energy, which is half mu squared cos squared theta plus the potential energy, which is, I omitted the 2, which is half mu squared sine squared theta over G. G has been cancelled. We cancelled out the G. So over 2. Okay. So we can factorize out half mu squared. Then within the bracket, we have sine squared theta plus cos squared theta. In trigonometry, sine squared theta plus cos squared theta is equal to 1. So since sine squared theta plus cos squared theta is equal to 1, when you put that here into the equation, you realize that the total energy of the body at the maximum height is equal to half mu squared. And this total energy is equal to the energy possessed by the body when it is just here. Okay, when it is at 1. Okay, so here, where's the duster? Here we look at just the velocity of projection. The velocity of projection U, not the horizontal, rather. Sorry, let me correct that. We look at the velocity of projection U. So half mv squared becomes half mu squared. And you realize that the velocity of the body at point 1 is equal to the velocity of the body at the maximum height. Confirming that in projectile motion, at every 2 points, the velocity of the projectile is conserved. What is here is equal to what is here. When it finally lands, just about to land on the ground, the total energy just before hitting the ground will be equal to the total energy at the maximum height. At every 2 points, the energy possessed by the body, okay, is conserved. This is the whole nitty-gritty about the energy possessed by a projectile. Already?
Mr. Dia, please I want to ask a question. So
Okay.
if, for instance, you are solving the M, what will it stand for?
M is the mass of the projectile.
Okay, thank you very much.
So define the variables. M is the mass M is the mass of the projectile. It has to be given to you. Okay. U is the velocity of projection. U is the velocity of projection. Theta is the angle of inclination. At every 2 points, the velocity of the body, the energy possessed by the body is conserved or constant. So no matter the points, the 2 points I choose, it can be here and here. The total energy possessed by the body here and the total energy possessed by the body here must be the same. And that is the conservation of energy in projectile motion. Okay. Do you have any more questions? No. This part taken by the projectile is described to be parabolic. Why parabolic? This is the reason. Please, do I clean everything?
Yes, please.
X. At any time t, the horizontal displacement is given by u cos theta times t. Then the vertical displacement y is given by u sine theta times t minus half j t squared. This is equation 1. This is 2. Let's make t the subject in equation 1 and substitute it into equation 2. T in equation 1 is equal to, yes, somebody should help me. T in equation 1. What's the value of t in equation 1? Adoma, Eresi, Inchira, Kestin, help me.
T is equal to x over u cos theta.
Thank you. So t is equal to x over u cos theta. When you substitute this into equation 2, you have u sine theta times x on u cos theta minus half j u x over u cos theta all squared. U will cancel u. Sine theta over cos theta is tan theta. So you have x tan theta minus half g x squared u squared cos squared theta. Now when you compare what we have to the equation of a parabola, y is equal to ax minus bx squared. This is the equation of a parabola. When you compare, in our case, because theta, the angle of projection, we know. So this part is constant. When we compare, we can say that this A is equal to tan theta. A is equal to tan theta. So tan theta is a constant because once you know the angle, you can find tan of the angle. Then D. Hello.
Please, I want to ask a question.
Go ahead.
Please, I want to ask where we had where we got the tan from.
Okay. Sine theta over cos theta is equal to tan theta. So when you divide sine by cosine of an angle, it's equal to tan theta. So sine theta divided by the cos theta is equal to this.
Please, thank you.
Welcome. So when you compare D is equal to half J U squared U cos theta all squared. Once U is the velocity of projection, cosine of the angle, once you know the angle, you can calculate it. J is also constant. So all these parts of whatever we have here is constant. So when you compare this to this, they are the same. All the adjournments are constant, which can be B. Okay. And so the equation of what we have is the equation of a parabola. And if you know these constants, maybe 2, maybe 5 or 3, whatever, and you plot x against y, a graph of x against y. When you plot this, you have a shape. This shape we are calling as parabola. In the same way, I said, since tan, all these are constant. When you plot ours, you also get the same shape. Hence, we say the path taken by the projectile is parabolic. The equation shows it. The equation for ours shows it. And when you plot, it will also give you this shape to confirm that this shape, which is our path, is the shape of a parabola. Are we okay?
Yes, please.
Okay. So basically, this is where we end projectile motion. We will move on to vectors. We will begin with vectors today.
Mr. Dear,
Hello.
there is the motion when you teach it. Like I understand, though, but when you give us question, then the formulas will start mixing in my head.
Okay. Uh, this is how to master. The key, you don't actually need formulas, but you have to understand how to get them. When you understand how to get them, you can easily recall. A projectile is at a two-dimensional projectile motion. As for the formulas, you can't learn them by rote. It is projected. That reminds me, there's another aspect when the body is projected from the ground. We have to also look at that part briefly. Okay. So the velocity of projection is this. I understand that because the velocity is given at an angle, it will be divided into 2 parts. The vertical part u theta and the horizontal part u cos theta. This is very, very key. This is very, very important. Now, you also need to understand that what we have is like this. vertical part, horizontal part. So u cos theta, u sin theta. The diagonal is the velocity of projection, which is u. By equal vectors, what I have here, I can bring it here. Once it has the same features as this one, same magnitude, same direction, this and this are parallel, I'm good to go. And this is perpendicular to the horizontal. So one other thing you have to understand is that, okay, then by Pythagoras theorem, this is u sin theta. By Pythagoras theorem, u squared, the square of this side is equal to the square of the horizontal u cos theta squared plus the square of the vertical u sin theta squared. And this is what we are calling as uy. This is ux. So it means that the velocity of projection u squared is equal to ux squared plus uy squared. This is very, very important because sometimes you can be given this, this, and be asked to find the velocity of projection. Please, are we okay? So when you are given this and this to find the velocity of projection, u is simply equal to the square root of Pythagoras theorem, square root of u squared, ux squared plus uy squared. So you have to understand this. Then in projectile motion, horizontal analysis, I know that whenever I'm looking for at any position of the body, if I'm to determine the horizontal displacement, because air resistance is neglected and gravity has no effect, then x at any time is equal to the constant speed u cos theta by the time taken for the body to get to a particular point. So you have to understand this. Please, girls, are you there?
Yes.
Okay.
Yes, please.
Okay. So I have to get this. You have to understand the range. The total horizontal distance range is equal to u cos theta times the time of flight. Okay. That's it for the vertical analysis. So you have for velocity, you know it is constant. Initial horizontal velocity is equal to final horizontal velocity, and they are all u cos theta. Acceleration horizontally is equal to what? Acceleration horizontal is equal to what?
Zero.
Zero. So you have this. You then look at the vertical analysis because of change in position both horizontally and vertically. So vertically, what happens? This is what will help you to master projectile motion. You understand whatever happens vertically, horizontally. Vertically, initial vertical velocity y. This is it. Initial vertical velocity is u sin theta. U sin theta. Because of the effect of gravity, as the body goes up, the speed decreases. What causes it? Gravity. So after any time t, the velocity will change vertically. So final vertical velocity is equal to the initial vertical velocity uy minus gt. You have uy, which is u sine theta minus jt v. So if I'm asked to calculate for the vertical velocity after any time t, this is what I use. Calculate for the vertical velocity after so and so time. This is what you use. But if it's about calculate for the velocity after this time, then you know that at every point in time there is a constant horizontal velocity, there is a vertical velocity. Okay. Time of flight. You know, at the maximum height, what happens? Yes, tell me. At the maximum height, what happens? Okay, before then, let's derive an expression for the displacement, vertical displacement. The vertical displacement is obtained using equation 2. U is equal to y is equal to ut minus half jt squared. Substitute u, initial vertical velocity. You see, once it's a y, it should tell you this is about vertical. Once it's about y. If it's h, h is height. The value is the same. If it is horizontal, you either see x or range. Please take note of this representation. If it's about horizontal, either x or range. So y h indicates that we are looking at anything vertical. So u sine theta sine t minus half jt squared. And this is the expression for the vertical displacement after any time t. These are the key stuffs. Okay, the next thing is using the same equations to get expression for the time taken to get to the maximum height itself, and then time of flight. So if it's about the time taken to reach the maximum height, you know, at the maximum height, what happens? What happens at the maximum height? Yes. Tell me.
At the maximum height,
At the
the initial velocity is equal to 0. So
take it again. At the
y
maximum
is equal
height,
to 0.
I don't want to come again. At the maximum height,
Vy
the
at the maximum
final.
height.
Mhm.
Pardon?
At the maximum height, the final vertical velocity is 0. Okay.
Yeah.
So Vy is equal to 0. If this is 0, then look at, you substitute 0 here into this and make t the subject. You substitute 0 in place of Vy and make t the subject. So 0 is equal to u sine theta minus gt. When you make t the subject, now t is equal to u sine theta over j. And you have the expression or relation for time taken to reach the maximum height. Time taken to reach the maximum. Hello.
Adjust to face the board.
I'm coming. I'll do so. So that is the relation for the time taken to reach the maximum height. Okay, this in some books is represented as T is equal to UY over G because they know UY is equal to U sine theta, the initial vertical velocity. Please, is that okay?
Yes, please.
Then if I want the time of flight, I know when the time of flight is the maximum time taken during the complete flight of the body. When the body starts from ground to ground, by the time the body gets to the ground again, the vertical displacement y, by the time the body gets to the ground again, the vertical displacement y is equal to what? Is equal to,
Please, the question again.
by the time the body, look at it, look at the diagram, starts and then drops to the ground again, the vertical, when it's here, it comes to the ground again. The vertical displacement y is equal to what?
0.
0. So if y is 0, when you use this, y is equal to u sine theta times t minus half j t squared. When you equate this to 0 and make t the subject, that t is equal to the time of flight, which I took you through, correct?
Yes, please.
So you have t to equal to 2u sine theta over g. As for that lengthy formula for the range is equal to, fine, we obtain u cos theta. Then when we factorize the time of flight, which is 2u sine theta, you don't have to worry yourself so much. All that you need to understand is that range is equal to u cos theta times time of flight. So instead of using this, I can use this to find my time of flight and then use r is equal to u cos theta times t. This would give me t. I just multiplied this by u cos theta to find the range.
Yes, please.
Okay. Yes, we will consider another dimension. We'll consider another dimension. Ground to height and height to ground. From what we've done so far, we are looking at ground to ground. Okay. Whoever asked the question.
Yeah.
Okay. So, and you see, if you use it, try solving questions with it, then you can understand very well. Okay. And this thing, you can also master it as you move on. From 1, from 2, this thing, as you go through, you solve problems. There's a hit, you come to us for guidance, clarification, you can master this thing. Okay, so don't panic. Okay, don't
Yes.
panic. Just try solving questions, it will be fine. All right. Then let's look at a projectile is fired. This time it is fired not on the ground, but it is fired from a height. Okay. We did a similar thing in vertically upward and downward motion. Do I clean it? If you won't respond, I'm even cleaning it.
Yes, please.
we did a similar one where in vertically upward motion, when we had considered the body being projected from the ground, getting to the maximum height, we also looked at the body being projected from a height h above the ground, if you recall. Okay, so this time the body is projected from the top of something and then gets to the maximum height and then drops to the ground. Okay, where this is given a initial velocity of projection u. Then this is the height of the tower. Then you were asked to calculate the velocity, the time of flight. Okay, the total distance covered by the body. Okay, from the ground. If you recall, we did a similar thing. And projectile machine, we're also going to look at the body being projected from a height above the ground. And what happens? So here we are looking at from a height to ground. Earlier, we saw ground to ground. So this is the ground. The projectile is fired from a height h above the ground. So from the ground to where the projectile is fired, it is h. Now it is fired at an angle. The angle to the horizontal. This is theta. The velocity of projection is theta, u, and the angle of projection is theta. And so there's the part, then it drops to the ground. Okay, so from this point to when it drops on the ground, height to ground, this is still the range. So if you ask, this is height to ground, okay? So
Yes, please.
what is the total distance? What is the time of flight as usual? So how do we determine these important details? And then the range. Okay, so let's consider the following, that from the maximum height to the ground, this is h. So this is h. Of course, once it is fired from here, I can determine, if the question is about determining the total distance, I know that when it moves from here to the maximum height, there's the maximum height. Okay, once I have this as let me use L. from what we've learned, the maximum height L is given by u sine theta squared over 2g. Okay, so if I'm to determine the total distance here, the total distance covered by the projectile when it is projected from a height to the ground would be equal to, look at something, it would have to move from here, come to the maximum height, then from the maximum height, drop to the ground. So if I know L, which is u sine theta over 2, u sine theta squared over 2g, this plus this total height h would give me the maximum height. Or if another dimension of this can be, I will go through this height, okay, move from here to this point, then this height again, so it has covered this side is here, okay, it will also move from that height to this level, so 2 times this, 2 times u sine theta all squared g over 2g plus from here to here is the height of the tower, which is given. The height of the tower is given as h. So plus h. Therefore, this and this will cancel. I have u sine theta squared over g plus h. So if it's about the total distance covered, this is how I can get that. Please, are we fine?
Yes, please.
Then, what about the time of flight? The total time taken to drop from the height from the tower to the ground. With the time of flight, if I could get the time taken for the body to move from here to the maximum height, which can be calculated from time taken to reach the maximum height, t is equal to u sine theta over d. So once I have u, I have sine theta, I can calculate the time taken to move from here to the maximum height. Don't forget, we are looking for the time of flight, capital T. So I have one aspect of it, which is t plus. The next thing I have to determine is the time taken to move from here to the ground. The time taken to move from here to the ground. Okay. And here, when the body gets to the maximum height and is dropping, the body will be free falling. The body will be free falling. So here, to get that, I mean the time taken to cover this height h. The time taken to move from the maximum height to the ground, which I've indicated as capital H. How do I do that? Okay, let's pay attention. I said when the body is dropping from the maximum height, the body free falls. So because
Please, we can't see.
from the maximum height, the body falls freely The velocity at the maximum height, the initial velocity u, is equal to 0 because the body would fall freely. If the body falls freely, then using y is equal to ut plus half gt squared, you can calculate for the time of flight, that the time taken to move from here to the ground. U is 0, so this part goes 0. What is y? Y is this height from the maximum height to the ground, which I can determine from the time taken to move from here to this level plus this. Okay, so all that I'm saying is that that distance or height is h. This is 0 because u is 0. Then I have half j t squared. If I make this the subject, t will be equal to 2 times h over g. And when I take the square root of it, I have 2h over g. And don't forget, this t is the time taken to move from the maximum height to the ground, which I'm calling as th. So if I want the time of flight is this t, capital T is plus t plus this. So I have my time of flight, capital T, being equal to t plus root of 2h over g. This will be the time of flight. So this is similar to what we've solved before and a vertically upward motion. Okay. All that you need to understand is still once it is projected at a certain height above it, okay, all your relations, time taken to reach the maximum height is intact. To move from here to here, it will take u sine theta. To move from the maximum height to the ground, you have to factor this total height. Okay. And when it is dropping from the maximum height to the ground, it is free falling. Okay. So I will send similar questions, a question on this, and then I think in our next in next week's meeting we can discuss to know maybe where you went wrong and all that, so you could master. Is that okay?
Yes, please.
So when it's projected from a height on, it's the same thing, but you need to understand how the whole thing also goes. Okay, vectors. 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 For vectors, we have to understand what do we mean by vector quantities. Yes. What is a vector quantity? What is a vector quantity? Yes. What is a scalar quantity? Yes, Adoma.
Mr. Chia,
Help me. What is a scalar quantity?
a scalar quantity is a quantity that has magnitude
Okay.
and
Example. Testing.
example.
Okay, testing has a problem with the microphone. Okay, Pia, go ahead.
Example distance.
Good. So here, these are quantities that have nothing to do with direction, only the amount or the magnitude. Okay, the amount or the magnitude. Let me have Stephanie give me another example. she made mention of distance, which is true. Stephanie. Oh, Stephanie is gone. She's gone to sleep. Okay, after that, go ahead. After that, go temperature. Good. So temperature. What else? If you have it, go ahead. Share with us.
Mass.
Mass. Good. Amount of time. Good.
Speed.
Amount of the substance. Speed. And a lot. And a lot. Vectors. A vector quantity. What is a vector quantity? Yes. If scalar quantities have nothing to do with direction and would only talk about the amount of the substance. Vector quantities, for vector quantities, we describe them by their magnitude as well as their direction. Okay, so give me an example of a scalar quantity. Sorry, a vector quantity.
Acceleration.
So acceleration,
Displacement.
displacement,
Weight.
Velocity.
displacement,
Momentum.
velocity, weight, force. So velocity, you said weight, force, and what?
Momentum.
Momentum.
Momentum. And moment. Moment. Okay. Good. Now, how do I distinguish a vector quantity from an impulse? We have a lot of them. We are impulse. Good. How do I distinguish a vector quantity from a scalar quantity? A distance of 100 meters is just the interval between the starting point, this point, and then measuring 100 meters from this point to this point. This is 100 meters. Quantitative. The quantity. Okay. Now, a displacement of 100 meters. How do I indicate it? Starting point, ending point. The interval between them, the 2 points is the distance. This is a displacement, so I have to indicate a direction. Maybe from A to B. So we are starting our measurement from a point A to a point B. If it's the other way around, this is it. This is a scalar quantity, just the interval between the point A and B. Distance. And this is a vector quantity, displacement. So when you are representing vector quantities, they are associated with magnitude and then direction. So we expect this bold line to represent the magnitude and then an arrow at the head or at the middle to indicate direction. Is that okay? So that is
Yes.
how to represent um scalar and a vector quantity. Oh, I'm coming. Somebody is complaining of having that challenge joining. But I think it's a network problem. All right. Vectors. Vectors is a topic you treat, okay, in a broader scope in maths. In physics, we apply vectors. So we look at when you have two or more vectors interacting, what is the effect? When the vector quantities are in the same direction or in the opposite direction, how do they relate? Is that okay? So a vector, maybe a force. It can be a force, it can be velocity, it can be acceleration, whatever. It's indicated as this. If I want the negative of this vector or this force S, when I take the same magnitude as this, but change the direction. So the negative vector, negative of a vector, maybe this is AB. I want to negate this vector. All that I do is that the same magnitude, but I have to change the direction. When I change the direction from this side, from this direction to this direction, I have minus of AB. So in negative vector, same magnitude, but you have to reverse the direction. Okay.
Yes, please.
Now, if I have two vector quantities, A and B, and in physics, we most often talk about forces, because a force is a vector quantity, and we mostly deal with force. So whenever we are treating vectors, we most often talk about forces. If I have two vector quantities or two forces exerted on a mass, in the same direction, this is F1, F2, this is the mass. The two vector quantities forces act on them. How do I get the resultant force? And what is the resultant force or the resultant vector? The resultant vector or force is defined as the singular force or vector whose magnitude or whose effect is equal to the combined effect of a number of vectors. So the resultant vector, instead of force, let me put vector, X is the similar force or vector whose effect is equal to the combined effects of a number of vectors. Meaning that what you as a single person can do, a number of people must do the same thing, or what the number of people can do, you as the individual can do the same thing. And that is what we call as a resultant vector. So if it's about resultant force, the resultant force is that singular force whose effect is the same as the combined effect of a number of forces. Please, are we okay?
Yes.
Yes, please.
Okay. So if we have two forces, F1, F2, acting on this mass, what happens? The resultant force is equal to here because all the forces are in one direction. It's equal to the summation of all the forces. Sum up all the forces. Okay. Summation of all of them. This is similar to when a car breaks down on a road and people are asked to help, okay, push it off the road. People come and once they are pushing it to a particular location, they combine their forces by pushing the car in the same direction. Okay, as they all push in the same direction, it's like combining their forces. And trust me, if it happens that they push the car from different directions, it will never go. Okay, so that if it's about the individual comes over, pushes it, it will not go. But when other people come on board and they add up their forces, now the total forces can overcome the weight of the car and then it moves. So when the forces or the vector quantities are in the same direction, the resultant force R is equal to summation of all of them. So here F1 plus F2. And when they are in the same direction, we say that they are acting in a parallel direction. They are parallel. So the forces, the number of forces of, let me use vectors. Vectors are in a parallel direction, are parallel when they are within a common direction. When they are within a common direction. And here the angle between the forces. When two vector quantities are parallel, please, what is the angle between them? Yes. What are you here?
Yes, please.
What is the angle between them? Akuya
0 degrees.
is 0. Yes. So when two vectors or vector quantities are parallel, the angle between them is 0. So when the angle is 0, then the resultant force is equal to the summation of all of them. So let's assume this is 10 Newton. This is 15 Newton. Then the resultant will be equal to 10 Newton plus 15 Newton, which will give us 25 Newton. The next possible question is that what will be the direction of the resultant force? Or what is the direction of the resultant force? Yes. What do you think will be the direction of the resultant vector or force? Opening question.
Please, the question
Yes,
again.
Clark. What do you think will be the direction of the resultant force?
In the same direction as
So exactly the direction of the forces. Good. Now, when they are oppositely. So the same forces, but this time there's the mass. We have one of the forces acting in this direction, F1, another one acting in the opposite direction, F2. Here, what do you think is the angle between the forces? What's the angle?
0.
What is the angle between the
180
forces?
degrees.
180 degrees. Okay. So when one of them here, when you measure this angle is equal to 180 degrees. How do we obtain the resultant force?
By subtracting.
So it depends. The resultant force will be the difference between the forces. So if F2 is greater than F1, then the resultant will be F2 minus F1. Okay, if F1 is greater than F2, then the resultant becomes F1 minus F2. 15 Newton, 10 Newton. The resultant here is equal to 15 minus 10, which is 5 Newton. Now, what do you think will be the direction of the resultant force?
It will follow the direction of the greater force.
Thank you. So, the direction of the resultant force will be here per our drawing on the board will be due west, because this is the east, this is the west, right? Or to the negative x-axis. Okay, the same situation, but this time this is what I have. I have F1, F2, then I have F3, F4, F4 is here, then F5. I'm to determine the resultant force and the direction of the resultant force. Yes, help me out. My task is to determine the resultant force and the direction of the resultant force. I'm
Mr. Job,
waiting.
did you say we should help you?
Pardon?
Please, did you say we should help you?
Yes, help me. I'm to determine the resultant force R and the direction of the resultant force. Uh-huh. Hey, the rest of you, what are you doing? Already, Fasti, Chrysler, Ellington, oh, Lynn, Millicent, Nanepia, Saida, help me. Kirsten, okay, Kirsten has a problem with the microphone. Yes, how do we obtain the resultant force? Every what? Okay, if you are ready, whoever is ready can share.
Mr. I don't know if what I have in mind is accurate.
Let's hear what you have in mind.
Okay, so I was thinking that
Mhm,
you first look for the first two forces to
mhm,
see the one which has a major impact, and then you
mhm.
first saw you saw for the second ones, and then the third one I'll assume there is an F6 which is 0.
You
So
are assuming. Mhm. Okay.
it means that that one is due to the last one is due to the um west, and then you sum everything up to see the major force like
Okay.
direction.
Thanks for your contribution. Please, who else? Let's hear from uh, another person. Every Abuatma.
Mr. Adrian.
I want to hear from you. Okay. I think we have about 10 minutes to go. So,
Mm,
in fact, as for from
Mr.
next
Dia,
week, hello, Ekuya, Ekuya Duma.
please you sum up all. Yes, sir.
Okay.
Please you sum
So,
up all the forces in one direction,
mhm.
then the other in the opposite direction. Then when you finish, you subtract the lesser one from the greater one to get the resultant vector.
Thank you. The same thing. You see, you are confused because over here I make the direction. You have two in this direction and then another one. And I'm sure that is the source of your confusion. Okay. All that you need to do is that identify all the forces in one direction, whether they are here or the other side. Identify all of them pointing to one direction. Sum them up. So let's look at those forces to my right. F1 is to my right, so F1 plus F2. Then let's come to the other side. This one is also to my right, F4. So plus F4. Assuming this gives me a maximum value, then I subtract, okay, the least sum from the maximum summed up value. So it means that here, my least sum will be all the forces to my left. So F3 plus F5. So when you are pushing a car, yes, ideally we expect all the forces to be exerted in one direction so we can move it. But if it happens that you distribute yourself, some in front, others at the back, when you push, the car will still accelerate to this arrangement, producing the maximum force. Is that okay? So if when we sum, this is greater than those ones in this direction, then this will be the resultant. The direction of the resultant is always to the direction of the larger force. Also, it's obvious the direction of the resultant will be all those ones to my right. Class, are we okay?
Yes, please.
Example, let's assume F1 is 5 Newton, F2 10 Newton, F3 6 Newton, F4 8, F5 10. Then F1 is 5, so 5 plus F2 10 plus F4 also points to this direction, so 8 plus 8. minus 3, 6, and 5, 10. So I have, this is 18, so 23. 23 minus 16, and the difference will be equal to, pardon?
7.
So 7, the resultant is 7 Newton. And the direction of the resultant will be the direction of the larger one, so to my right. So a question can mix them up, but you will have to sum up all the forces in one direction, sum up all the forces in the opposite direction, and then subtract. Any question?
Yeah,
Any
please.
question? All right. So this is where we end today's show. Thanks for being around. Please, my assignment, I'm going to update those who have sent theirs to me. Mark and get back to them. Okay. So do well to submit your assignment. Okay. So we'll have
Yeah.
another session next week. Okay.
Mr. D,
Hello.
please, me, I'm a Kosiaduma, not a Kiaduma. You keep
I
calling me a Kia.
because you are noted. Okay.
Yes.
All right. Thank you. All right. Yo, see you next week. Have a wonderful week. Okay. And
Okay,
take
you
care
too.
of take care of yourselves too.
Yes, please.
Bye bye.
Bye.